All right, welcome back. Today we are diving into a super weird paradox at the very heart of modern AI. It's this problem that seems so simple, but it's been like an invisible wall, just holding back major progress for years. I mean, really think about this. We've got AIs that can crush the bar exam, they can write really complex code, they can even nail medical diagnoses. And yet, if you ask one of these brilliant AIs to just read a long book and tell you what happened, it completely falls apart. It starts forgetting characters, mixing up the timeline, or just totally loses the plot. So how can something so incredibly smart have such a terrible memory? Well, that's the big mystery we're going to solve today. So before we get to the really cool fix, we got to understand what's actually broken. And this isn't some simple bug, it's a deep, fundamental limit in how these things are built from the ground up. It really all comes down to this thing called the context window. The best way to picture it is to think of the AI's short-term memory as a desk. You can put a couple of books, a few papers on it, and you're good to go. But what happens when you try to pile on an entire library? Yeah, stuff starts falling on the floor, you can't find anything, and pretty soon the whole desk is totally useless. That right there is an AI's context window. But here's where it gets really bizarre. There's this other problem called context rot. This means that even if you somehow manage to cram all that information onto the desk, the AI actually gets dumber. It's wild. It starts to forget the very first thing it read, or it just gets confused trying to juggle too much at once. It proves that just building a bigger desk isn't the answer. And we are not talking about a small dip in performance here. The research shows that with the most advanced models, when you give them more and more information for a complex job, their accuracy doesn't just kind of drift down. No. It falls off a cliff. I mean, it goes from pretty good to completely useless, fast. And that is the wall that researchers have been slamming into over and over again. So if you can't just build a bigger memory, what's the move? Well, a recent paper from some brilliant folks at MIT came up with a totally different way of looking at it. It's one of those ideas that's so smart and so simple, you kind of wonder why no one thought of it before. This is the big aha moment. See, the old way was called in-context reasoning, which is basically just trying to brute force the problem, shove everything into the AI's tiny memory and hope for the best. The new way is called environmental interaction. Instead of forcing the AI to memorize the entire book, you just give it the book and teach it how to look stuff up. It's the difference between a brutal closed book final and a much more sensible open book exam. And this awesome new approach, it's called Recursive Language Models, or RLMs for short. And this is the tech that seems to have finally cracked the code on AI's memory problem. Okay, so how in the world does this actually work? Well, the big idea here is just so clever. You teach the AI how to hand off the hard parts of a problem to copies of itself. It's like turning the AI into a super efficient project manager. So check this out. The main AI, let's call it the boss AI, it never even tries to read the whole giant document. Instead, it treats that document like a file sitting on a computer. From there, it can write little bits of code to search the file, and when it finds a section that needs a closer look, it just delegates that small task to a fresh copy of itself. Okay, so step one is all about filtering. The AI doesn't just read, it searches. The boss AI writes a little script to scan the entire document for specific keywords it's looking for. This is how it can take millions of words and instantly narrow them down to just a few relevant paragraphs. It's the definition of working smarter, not harder. Then, once it finds a chunk it's interested in, it moves to step 2, decompose. This is the recursive part. It makes a recursive call, which is really just a fancy way of saying it hands off that small piece of text to a helper AI with one very specific job. Like, hey, in this paragraph, just find the winner's name and report back. It's breaking a giant, impossible problem down into a bunch of tiny, easy ones. And finally, step 3 is to stitch it all back together. The boss AI acts like the manager, just collecting all these little answers from its team of helpers. Then it uses code to assemble all those little pieces into one big final answer. It builds the complete picture without ever having to actually hold the whole thing in its memory at once. So, the theory sounds amazing, right? But does it actually work in the real world? Well, to find out, the researchers put these RLMs through an absolute gauntlet, a series of incredibly difficult tests designed to make them fail. And trust me, they did not pull any punches. They tested things like doing research across 1,000 different documents at once, understanding the logic of a massive software codebase, and even these really nasty tasks that get exponentially harder the more data you add, like having to compare every single sentence in a book
to every other sentence.
And the results? Honestly, they're just staggering. On that hardest task, the regular super advanced model scored 0.04%, basically zero, a total failure. But the RLM, using that exact same model as its brain, scored 58%. That's not an improvement. That's the difference between totally impossible and solved. And that wasn't just a one-off either. Just look at this table. On a research task with 1,000 documents, the base model just crashed. It hit its memory limit and scored a big fat 0. The RLM, 91%. On understanding a complex codebase, it more than doubled the score. The pattern here is pretty clear. Okay, so there's got to be a catch, right? And there is. In this case, it's cost. For a simple question, an RLM costs about the same as a normal AI. But because it can create these really long, complex chains of helpers calling other helpers, a really tough problem can get a lot more expensive to solve. So you're basically trading a variable cost for a gigantic leap in what the AI can actually do. So let's step back from the charts for a second. What does all this actually change? What does it mean for the real world, now that AI can suddenly remember and reason over these huge amounts of information?
Well, what it means is that we are watching a fundamental shift in what an AI even is. It's transforming from a tool that can answer a quick question into a system that can basically run its own deep, complex research projects, all by itself. This unlocks stuff that was basically science fiction just a little while ago. Imagine an AI that can comb through every single line of code a company has ever written to find one tiny bug, or a medical AI that can review a patient's entire life story of medical records to spot a pattern no human could ever see, or maybe an AI that can finally read a whole library of books and tell you what's in them. These aren't just small improvements. These are brand new things that are now possible. The researchers themselves put it perfectly. I'm just going to quote from the paper because it's so good. The key insight is that long prompts should not be fed into the neural network directly, but should instead be treated as part of the environment that the LLM can symbolically interact with. It's all about changing the AI's relationship with its data from memorizing to interacting. And let's not lose sight of just how big this jump is. We're not talking about a 20 or 30% bigger memory. This RLM method successfully handled tasks with inputs that were 2 orders of magnitude. That's 100 times larger than the AI's built-in memory limit. It's a truly massive leap. And that really brings us to the final thought. You know, the craziest part of all this isn't just that it solved the memory problem. It's that the AI, by learning to delegate and break down problems, is basically teaching itself a new way to think to get around its own flaws. So the real question this leaves us with is, if an AI can now learn to tear down its own invisible walls, what walls are going to fall next?